I'm an associate professor here at Institute of Informatics, University of Warsaw. I'm also a data science lead at Google Cloud Warsaw, where I lead a small team that optimizes recommendation and automation products in Google Cloud. So today I will present my research topics that center around computational infrastructure. So cloud computing and supercomputers and data centers. Why should we bother with computational infrastructure? Why do I? Because these supercomputers and data centers basically run the world, and they have enormous impact on our daily lives. So most of you probably know that behind every app that you have on your smartphones, there is a data center, and that provides most of these app services. So data centers store YouTube videos, route your navigation in Google Maps, or store and provide music when you listen to Spotify. But perhaps almost as importantly, there is a supercomputer behind many modern scientific discoveries. What you see here is the first ever picture of a black hole. And to make this picture from an array of telescopes, the researchers used a supercomputer. And basically, a supercomputer is currently like a standard research tool in many branches of modern hard sciences, like astrophysics, climate research, biology, chemistry, astrophysics. Again, what you see here is a simulation of evolution of a galaxy. But supercomputers have been with us for the last 30 years or so, and data centers for the last 15 years or so. Why now? I believe that, so why bother with these topics now? I believe that we come to a very important moment in the evolution of this hardware and software, that there is first of all, because of the economies of scale, these machines are getting bigger and bigger. It's much cheaper to operate yet another cluster of 10,000 nodes when you're Google than to build your own small cluster of 1,000 machines that you hide somewhere in your basement. And this is very similar in supercomputers. But more importantly, there is also unification of software systems and software stack that runs runs on this hardware. So roughly 60 to 70% of top 500 academic supercomputers in the world run the same open source cluster scheduler called Slurm. This is the same cluster scheduler that we use here at the faculty for scheduling jobs on our small GPU cluster. And with data centers, the state of the art is similar. For instance, all Google data centers run on Borg, which is an internal Google scheduler. But Borg, in its architecture and its constraints and its way of managing resources, is very similar to open source Kubernetes. So if you play with Kubernetes, you can have similar similar problems to what Google has in Borg. Again, why now? There has been a revolution in using machine learning, and in particular deep learning, for many applications in computer science, and in particular for image recognition. But in this domain, managing infrastructure, these methods are only starting. What you see here are two pictures from our two recent papers. where we show some very simple statistical methods that where we analyze traces published by major cloud providers, Azure, Microsoft Azure at the right, left, and Google Cluster Trace at the right. And we show that it's, for instance, in Google Cluster Trace, we show that while it's very difficult to find out what would be the CPU usage of a single task in a cluster, once you pack a dozen of these tasks together, you can use a very simple statistical method, the central limit theorem, to approximate the overall load. And I will go back to this result later on. But so you can think that, okay, it's very easy to get a PhD now in this domain, because we just can take what has been proposed in image recognition and use the same method in let's say data center scheduling and have great results. And basically we can solve every single data center scheduling problem with deep neural networks. This is not the case, and this is where this problem gets interesting. On the left, you can see the average accuracy of solutions in the ImageNet competition. So this was one of these early competitions where you had a bunch of pictures and you had to assign labels to these pictures. So basically labeling that there is a picture of cat, so you put that it's a cat on, or there's a picture of dog and you put, hey, there's a dog. And back in 2017, organizers figured out that majority of the entrants had an accuracy greater than 95%. So they decided it's time to end this contest, because like going beyond 95% accuracy doesn't make sense. It's just overtraining. What's 95% accuracy in computational infrastructure? As the name suggests, infrastructure is below layers and layers of software. So what we need in infrastructure is very high quality of service. Just as an anecdote, last December we had a huge outage at Google. One of the internal systems that manages authentication for users went down, and basically you couldn't make any action as authenticated Google user for more or less 45 minutes. And this 45 minutes was enough to generate headlines in major newspapers around the world, right? 45-minute outage is averaged over a year, means 99.99% availability. And this is basically what is our goal in computer infrastructure, methods that are highly available. Why to do a PhD with us? We are experienced, we have lots of domain knowledge, and we have lots of new ideas. Our team is currently composed, so I'm leading the team. I have a fourth-year PhD student, Paweł Żuk, who is going to graduate next year. And we also collaborate with a postdoc this year and next year, Bartek Przybylski. So my background is, I've been doing this kind of research for the last 15 years. I did my PhD in Grenoble in France on scheduling in academic clouds. Then I did a postdoc in Singapore. I've been at University of Warsaw since 2010. I did my habilitation 5 years ago. I joined 3 years ago. I joined also Google Cloud Warsaw. When I first joined as a visiting researcher, I'm since October 2020. I'm data science lead. Paweł, our PhD student, now specializes in function as a service scheduling, and Bartek did his PhD in more formal approaches to scheduling. It's called operational research. So I believe I cover this whole scope of this problem. what will you learn? So I believe that PhD is 3, 4, or 5 years of very intensive learning, and basically you will end with a like very first-hand knowledge of using scientific method in large-scale systems problems. So it's, imagine you have a difficult systems question, and you have an idea like how to schedule jobs in a Google cluster, right? And you have an idea of an algorithm. You start with a naive algorithm, and you have a slightly better algorithm. How would you compare these algorithms? How would you convince yourselves, your colleagues, your reviewers at the conference that this approach is good enough, that this approach is better than some of the old approaches? So most of you are familiar, especially this faculty, with some theoretical guarantees, and we do this too. So for some limited problems, like very restricted versions of these problems, we can actually prove that an algorithm is, let's say, 2 and 5/6 approximation, which is this paper, and this is better than the previous algorithm, which was 3 minus 1/m approximation, right? But sometimes these theoretical guarantees are made in a model that is very restricted, and it's quite far from what's actually going on in the systems. Second, this theoretical guarantee is the worst case guarantee. We usually expect that in the average case, the algorithm will perform much better than 3 or 5, 2 and 5/6 times the optimal solution. So we do simulations. And doing simulations is also non-trivial, because you have to think about finding a right trace for that you play in your simulator, measuring measuring the quality of your solutions, making all the studies of changing parameters and figuring out how these parameters, or how the parameters of the instance change your results. And finally, and what's the perhaps most entertaining part in this kind of research, are experiments on real systems. You can, thanks to this, thanks to the fact that most of these schedulers are open source, you can actually implement your solution in the real scheduler, and then deploy it to a real system and emulate it, or even use it on a real system. A few years ago, my master's student deployed a scheduler to one of clusters, supercomputers at the Warsaw local supercomputing center. What you see here on the right bottom is our most recent paper with my Google colleagues, where we deployed a new way of estimating limits on the load of a single node in a Google cluster. And we deployed this to over 10,000 machines in a Google data center, and measured that our method gives roughly 6% more load per node than what currently is used by Google. And this method is based also on this simulation study that I showed earlier on. So that's all. I will be here during this break after these sessions. Come talk to me if you're interested. And there is also a link to my homepage with our recent publications, and my email if you prefer to asynchronous contact. So thanks for your attention.